Jai Hind. Today we are going to discuss rings and fields, the two algebraic structures. As we know, rings and fields are algebraic structure with two operations, additive operation and multiplication operation. So we will discuss here in this particular lecture what are rings, what are the properties that should be satisfied by the set with the two operations to form a ring, when it will be a field, what is integral domain, and then at last we'll discuss few elementary properties of the rings. So let us start with the topic. So here I am starting with rings. So now what we are given R, a non-empty set with two binary operations. One is additive operation and one is multiplicative operation. So our algebraic structure is the set R with addition operation plus and multiplication operation multiply. So we are having two categories of operation here, additive operation and multiplicative operation. Now when this set R with these two operations will form a ring. So these are the axioms that should be satisfied by the ring to form, by the set to form the ring. Okay, so we are given two type of operations. So one we are representing with addition, that is plus sign, and another we are representing with multiplication. We can use this notation or simply we can use this notation. So what are the axioms that should be satisfied by the set and the binary operations to form the ring? So we have listed here 6 operations. The first operation is associative property with respect to addition. So what is the first condition? The additive operation should be associative in nature for this particular set. So what is my set? My set is R. Let me take 3 elements A, B, C from R. Then what should we have? Associativity true. That is A plus B plus C should be equal to A plus B plus C. It means the addition operation should be associative in nature. So this is associativity with respect to addition operation. Addition operation is associative in nature. Second, what is our second property for ring that should be satisfied? We should have an element belonging to R. What type of element? Zero element we call it, but what type of element? That is identity element with respect to the addition operation. So there must exist an element 0 belonging to R such that for every A belonging to R, A plus 0 is 0 plus A is equal to A. It means there should be identity element present with respect to the addition operation. Third property. Again, it is a property related to addition operation. So second was identity element with respect to addition, and third we will talk about inverse element. We are having two operations here. The identity we just talked about is with respect to addition, and now with respect to addition we are talking about inverse element. For each A belonging to R, there must exist an element minus A belonging to R. It means negative element of A. This is called the negative of A. What it is? It is additive inverse. What does it mean? It means that A plus negative of A should be equal to negative of A plus A is equal to 0. So this is inverse property with respect to addition operation. Now what is the fourth property? That is commutative. The addition operation should be commutative in nature. For any AB belonging to R, we should have A plus B is equal to B plus A. That is commutativity. So in short, we can say the set with respect to the addition operation, the properties that hold are associative, identity, inverse, and commutative. Now, the fifth property is with respect to the second operation. The second operation is multiplication operation. So when we are taking multiplication operation with the set, then we should have the associativity true with respect to multiplication. So fifth property is associativity with respect to multiplication. That is, for any ABC belonging to R, we should have AB into C is equal to A into BC. So we have seen here that both the operation must fulfill the associativity property, addition as well as multiplication. The last property for ring should be distributivity. The multiplication operation should be distributive over addition. Multiplication should be distributive over addition. That is the requirement to be a ring. What does it mean? It means distribution of multiplication over addition. It means A into B plus C should be AB plus AC. And if we take on right hand side, this is the right distribution. B plus C into A is equal to BA plus CA. So if these properties are true, then the set with the two operations form a ring. We can see example also. If we talk about set of integers with integer addition and integer multiplication. Set of integers with integer addition and integer multiplication. If we see this, we can check that addition over integers. If we add integers, then it is the integer addition is associative in nature. Okay, so the first property is true for integers. This property holds. If we talk about second property, what is second property? There must be zero element. And we know that 0 is an integer. 0 belongs to Z. So 0 is an integer such that if we add 0 to anything, any integer, the result will be the same integer. So this is identity property of addition of integers with respect to addition. Now if we check the third property, what does the third property say? It says that we should have negative of each element. So if I take any integer, let me take any integer A. What is negative of A? It will be minus, that is negative of A, and we will get 0 in answer. So it means we have to check if A is an integer, minus A is integer or not. And we know that if 2 is integer, minus 2 is also integer. If minus 3 is integer, 3 is also integer. It means the inverse property holds for integer with respect to addition. So our third property also gets satisfied. Now next, what is the next property? The next property is commutativity. We need to check that if we add two integers, A and B, whether we add A to B or B to A, we will get same answer. That is, integer addition is commutative in nature. 2 plus 3 is same as 3 plus 2. So commutative property also holds. So we can see that all the four properties are true. So we have checked the four properties, that is associativity, identity, inverse and commutative with respect to addition operation. Now if I check the properties that should be true with multiplication, that is associativity. We know that integer multiplication is associative in nature. That is 2 into 3 into 4 is same as 2 into 3 into 4. Whether we multiply 2 and 3 first, then we multiply with 4, or we multiply 3 with 4 and then we multiply with 2, will get the same answer. So associativity also holds for multiplication. And what is the last property to be checked? Distributive. Multiplicative operation should be distributive over addition. And we know that integer multiplication is distributive over addition. So all the properties holds for this particular algebraic structure in which the set of integers is present. The set is set of integers and operations are integer addition and integer multiplication. So it forms a ring. This is one example of ring. Okay. What are other examples? Other examples we can take at Z6 plus 6 and multiplication 6. That is modulo set with modulo addition and modulo multiplication. All these form an algebraic structure which follows all the properties, that is associative, identity element, again 0 is the identity element. The inverse, what are the inverse element of Z6? For example, in an integer, the negative means if a is there, minus a is another integer and a plus minus a is 0. From here we can see that in Z6 we are having the elements 0, 1, 2, 3, 4, 5. This is the modulo set, the residual when we divide with 6. So 0 is inverse of 0. 1 is inverse of 5 because 1 plus 5 is 6. 6 modulo 6 is 0 and 0 is the identity. 2 is inverse of 6. So we call it negative of a. What is minus 2 here? What is negative of 2 here? That is 4. Why? Because 2 plus 4 is 6 and 6 modulo 6 is 6 mod 6 is 0. So negative of 2 is 4. That is the additive inverse. 3 is inverse of itself. 3 plus 3 is 6. 6 mod 6 is 0. So we can see that 0 is inverse of itself. 3 is inverse of itself. 2 is inverse of 4. 4 is inverse of 2. 1 is inverse of 5 and 5 is inverse of 1. So it also forms a ring. If we take another set, that is set of real numbers, in set of real numbers also, if we take the two operation as set of real numbers with real addition and real multiplication, that will also form a ring, because all these properties also holds for both the operations, that is addition and multiplication with real numbers. Now we'll study few special type of rings. What are the special type of rings that we'll talk about, which are having some additional properties. If we talk about a ring R, we have just seen on the last slide that with respect to addition, it will be associative, commutative, it will have identity property, and it will have the inverse property true. It means identity element exists as well as inverse element exists. Now, if we talk about the second operation of the ring, what is the second operation? That is multiplication. With respect to multiplication, the ring is associative, and the multiplication operation is distributive over addition. If commutative property also holds, it means if A into B is equal to B into A for all AB belonging to R. That is the commutative property with respect to multiplication. then OR is called a commutative ring. If the commutative property holds for multiplication operation also, then we call it a commutative ring. Second is a ring with an identity element 1. Now we are talking about multiplicative identity. The additive identity must be there. It is a ring if the 0 element is present. What is 0 element? That is additive identity. If we are having one element which we call here identity element, such that A into 1 is equal to 1 into A is equal to A for all A belonging to the set R, the ring, then we call ring with an identity element. Let us repeat again. What the point is, ring has additive identity, and if it has multiplicative identity also, then we call ring with identity element. Okay, and next is the property that talks about inverse element. We know that in a ring, additive inverse is there for each element, but if we have multiplicative inverse also, then we have a special kind of ring. Okay, so if we are having an element A belonging to R and it has multiplicative inverse, we are having two operation, addition and multiplication. So for the elements which are having their multiplicative inverse also, those are called units. An element A belonging to R is called a unit if it has a multiplicative inverse, that is, it is having an element such that A into A inverse is equal to A inverse into A is equal to 1, the multiplicative identity. Now, what are zero divisors? We are having a ring. In ring, if there are some elements which are non-zero, but their product is 0. If the elements are non-zero and their product is 0, that we are talking about. Okay, so what is a ring? R is called a ring with 0 divisors. R is called a ring with 0 divisors if there exists non-zero elements A and B such that A into B is 0. So what we have taken? Two elements from the set R which are non-zero but their product is 0. Then we call A and B 0 divisors, and ring is called ring with 0 divisors. So we have studied here special kinds of rings: commutative ring, ring with identity element, ring with units, and ring with 0 divisors. Now, after studying these properties, now we'll talk about integral domain and fields. A commutative ring R is an integral domain if R has no 0 divisors. R has no 0 divisor means AB cannot be 0 if A and B both are non-zeros. Reverse order we can say, in reverse order we can say AB is 0 implies either A is 0 or B is 0. It cannot be there that the two non-zero elements are multiplied to give the multiplication answer as 0. Then we call it integral domain. So let us understand with example. If I am having a ring with set of integers plus operation and multiplication operation, then I am not having any two integers A and B such that A into B is 0. There doesn't exist A, B such that A is not 0, B is not 0, but AB is 0. No two non-zero integers got the multiplicative answer 0. If the multiplication answer is 0, if AB is 0, then definitely either A is 0 or B is 0. If multiplication of two integers is 0, it means one of the integers is 0. Otherwise, it is not possible. Okay, so it is an integral domain. This particular ring is an integral domain. If I talk about the second ring that we took as an example, that is modulo set with 6, modulo addition, modulo multiplication. This is also a ring. But in this ring, what is there? There are two elements, 2 and 3. What are 2 and 3? These are the two elements which are non-zero. But what is multiplicative operation here? That is modulo 6 multiplication. When we apply modulo 6 multiplication on 2 and 3, we get the answer as 0. So what we are getting the multiplicative answer 0 while both the operands are non-zero, 2 and 3. So this is not a ring with 0 divisor. It is a ring with 0 divisors. It is ring without 0 divisors. So it is not a integral domain. It is not an integral domain. This one is integral domain. Why? Because if multiplicative answer is 0, then either of the operands will definitely be 0. Either A or B or both. But at least one will be 0. Only then we can get 0 in multiplication. Filled. Now, if we have a commutative ring, it means ring is there. Ring is there means all the 4 properties are true with addition. What are those? Associative, commutative, identity and inverse. With multiplication, all the 4 properties. With multiplication, we have the associative property true. Now, if this particular ring is commutative also, commutative means A into B is equal to B into A. It means the multiplication operation is also commutative. And there is one identity element also, that is 1. It means if it is commutative and has the multiplicative identity, is called a filled if every non-zero element A belonging to R is a unit, that is has a multiplicative inverse. So if I check Z plus multiplication, in this particular set, I am having the commutativity true with multiplication. I have identity element 1 because 1 is integer. But all the non-zero elements doesn't have multiplicative inverse. For example, 2. The multiplicative inverse of 2 will be 1 by 2. Okay. But 1 by 2 doesn't belong to Z. So this is not forming a filling. It is forming integral domain. Why it is forming? Because no two integers got the multiplicative answer 0. Cannot form 0 after multiplication if neither of them is 0. Okay. Now if I am having set of real numbers with multiplication and operation, with addition and multiplication operation, then it is a ring which is having multiplicative, commutative property true, it is having 1 also, that is the identity element with respect to multiplication. And every non-zero, there is one element in R only which is not having the inverse element, as 1 by 0 is undefined. Otherwise, all the elements are having the multiplicative inverse. So it forms a field. But here multiplicative inverse is not there. So it is not a field. It is not a field and it forms the field. So this is our field. So we have talked about definition of ring, field and integral domain. Now we'll study 3 properties of rings. If we are having any element A from the ring and it is 0 element. 0 element of the ring means additive identity of ring. And if we multiply any element with 0 element, then in answer we will get 0. Definitely for each ring, if the 0 element will be multiplied with any other element, then in answer we will get 0 element. How can we prove this? Because 0 is identity element, so we can write 0 is equal to 0 plus 0. Because whatever we add to 0 will get same in answer. So here what I am adding? Identity to identity, 0 to 0. So definitely I'll get 0 in answer. This is the identity property. Okay. Now there is another operation in ring, that is multiplication. So that I am using here because I have to prove A into 0 is equal to 0. So I am taking this left hand side with multiplication operation. A into 0 is equal to. So what I have done, 0 can be written as 0 plus 0. So I replaced it with 0 plus 0. Now because it's a ring, so distributive of multiplication over addition is there. So after applying the distributive operation, I am getting A into 0 is A into 0 plus A into 0. Now because it is a ring, so additive inverse is there. So by applying additive inverse on both the side, I just added the additive inverse on both the side. So additive inverse of this will be added to this. So what we'll get in answer, that is identity element. That is the inverse property. Same way here, we will get 0 plus A dot 0. So we'll A into 0. So we'll get A into 0 in answer. That is what we wanted to prove. Same way we can show that the multiplication of A with negative of B. The multiplication of A into negative of B is same as negative of A into B. Same way, negative of A into B is same as negative of A into B. We can show like this. We know that when we add B with negative of B, we get 0 in answer. That is the additive identity. So if A into negative of B, as we have seen on last slide, is negative of AB, it means if I will add this to negative of AB, I'll get 0 in answer. So now let us check. AB plus this is equal to A into B plus minus B by applying the distributive property. So by applying the distributive property, I have taken A distribution over B plus minus of B, that is negative of B. And we know that B plus negative of B is 0, that is the identity element. So A into 0 is 0, we have just seen. So we got 0 in answer. When it will be actually negative of A, when we get 0 both after applying both sides. So if I apply now in reverse order, that is A minus B plus AB. Then again after applying the distributive property, I'll get A into minus B plus B, which is 0. So I'll get A into 0 is equal to 0. So we can say here that it is negative of AB. It means by taking the inverse, additive inverse of B, multiplying A with negative of B, is same as if we find negative of multiplicative answer of A and B. Okay, and the third one is if we multiply negative of 1. What is 1? 1 is the identity element. This will be true when R is there, R is having the identity element 1. It may be the case that the ring is not having identity element 1. So for that, it is not true. We are talking about a ring that has a identity element. So the negative of 1 into A is negative of A actually. So let us prove it. So if this will be negative of A, then we will add that to A, will get 0 in answer. So and now let us try. A plus minus 1 into A is equal to this. What we have done here, because it is having the identity element, it means A is equal to 1 into A. So 1 is there, so that is the identity element. So what we got, 1 into A plus minus 1 into A. After applying the distributive property, what we will get, 1 plus minus 1 into A, and which is 0. And 0 into A is 0, we have just seen. Same way, we will see minus, when it is additive inverse, when A plus minus A is 0 and minus A plus A is 0, both sides. So now we are checking in the other order, reverse order. Negative of 1 into A plus A is equal to minus 1A into A is 1 into A. So here applying the distributive property, we are getting minus 1 plus 1 into A, which is 0 into A, 0. So from here we can see that the multiplication of negative of 1 into A is negative of A. So we have started three proofs here, 3 theorems here, which are based on our rings. So in this particular lecture, we talked about introduction of rings, fields and integral domain, and what are the axioms that should be fulfilled, that should be satisfied to form a ring. What is integral domain? There should not be zero divisors. Two elements are zero divisors if their product is, their multiplicative answer is 0. Multiplication is 0, as we have seen in modulo set. 2 and 3 both are non-zero, but when we multiply 2 with 3, then we get 0 in answer. Then we talked about fields definition and introduction. Thank you. Jai Hind.